Hello, Algebra 1. Today we're looking at 4.7 applications of exponential growth and decay. And I actually like this lesson quite a bit. I like this topic. It's so applicable to so many different fields of study, and I think it's really going to benefit you. So to begin with, we are talking about exponential functions, so I want to go ahead and write down the model for that we've been working with. That's it right there. A is your starting amount, but oftentimes it's your y-intercept. And then B is going to be your basically I'm going to call it your growth or decay factor. And so exponential growth functions, a quantity is growing exponentially if it increases by the same percent in each unit of time. So some of the things that we've looked at so far would have been accurate for modeling things that like double in value or cut in half in value. But most things that grow by a little bit at a time. So like if you've got a puppy, it grows fast, but it doesn't double in size, in a week or whatever. It grows by maybe, it might grow 20% in a week. And so this is a way to incorporate those little bits of growth into an equation. So here we go. Let's do this. The new formula is just an adaptation of this formula. Instead of A, they use C. But that's your starting amount. I'm not sure why they use C, I'll be honest. And then because you're growing a little bit, you're not doubling or tripling or whatever, you're growing a little bit. So you've got your original amount plus you're growing a little bit. So that's going to be your growth factor, is when you add 1 plus the rate at which you're growing. And then you're going to have a time. So yeah, C is the initial amount. And same as A, initial amount or the y-intercept. R is going to be the rate of increase. And it's going to be a decimal, so be wary, okay? They're going to give it as a percent, but you're going to write it as a decimal. And then T is, of course, time. Okay, and we can use this formula for all sorts of things. If it's a decay function, it's going to be a quantity that is growing exponentially. It's actually decaying. We should say it's decaying exponentially if it decreases by the same percent in each unit of time. And, it just changes this a little bit because instead of being cut in half or something like that, or a third or fourth, you may be decreasing by a little bit. Maybe you're on an eating dietary plan or something, and you're losing a little bit of weight. Well, you're not cutting your weight in half, even in a year, right? That might be bad news. You're not cutting your weight in half, but you may be, losing 12% or 5% or 3% or 0.05%. And so because you're losing it, we write this as a minus the rate that you're losing. And then that gets you your decay value. So everything is the same. Okay, so they've got some steps here that they give us that we can use to write these out. So yeah, and these are good advice. It says decide if it is growth or decay by looking at keywords. And then plug the numbers in, substitute the numbers into the correct places. And they remind you, be sure to change your percent to a decimal. And then you solve the equation, and this says to round to the nearest hundredth, but sometimes the problems will specify something different. All right, so example 1, you buy a car for $12,000. Suppose the car depreciates at the rate of 20% per year. write an exponential decay model for this situation. So that's one of your objectives, is to write a model. Then you're going to find the value of the car after 5 years, and this is good stuff here. Okay, so hopefully you've heard of depreciating. That just means you bought something and it decreases in value. And so we know we're going to use y equals c1 minus r to the t, and we got to fill in the initial amount. We got to put in the rate. So 20% divided by 100 is 0.2. That's what we're going to use, 0.2 in this formula. And then time. So that's our equation. But now they want us to find out how much the car is worth after 5 years. Now this is where you got to be careful, and depending on what calculator you have, you're going to do things a little different. Let me grab a calculator real quick. So on this calculator, and on calculators like this where you can't just enter some of your calculators, you can enter this all in exactly as it is and it'll spit out the right answers, so that's cool. But on a calculator like this, I got to be really careful, because if I do 12,000 times 1 minus 0.2 to the fifth, it's going to think I'm just doing 0.2 to the fifth. It's going to get confused. So what I like to do is I'll evaluate this first. Oftentimes I'll do it in my head. That's going to be 0.8. So I'll do 0.8, and then I'm going to do order of operations. Next would come the fifth power. And then finally I would multiply, oh, I pressed the wrong button, sorry. 0.8 to the fifth power. And then I would multiply by 12,000 to get the new value of the car. So after 5 years, this $12,000 car is no longer $12,000. It is $3,932.16. So yeah, it's pretty cool. I really like using these formulas to figure these problems out. It's fun. All right, example 2, you deposit $600 in a bank that pays 4%. Sorry, there we go. Pays 4% interest compounded yearly. Find the balance after 12 years if you leave the account alone. Okay, so class, there's a few things here. Banks, you can deposit money in a bank and they'll pay you for it if it's a savings account, or you do a certificate of deposit. But anyway, in a savings account, they're going to add the interest back into the money that you put in, and then that money, that interest that you earned is also going to grow. Well, they're saying that they're going to add that interest in just once a year. There are different accounts that will do it different, more times in a year, and so that they, if you're doing it every month, it'd be compounded monthly. So the same formula can be adapted for those situations. But they're just compounding yearly, and so this is going to be a typical sort of thing where it's growing 4% per year. All right, so it pays, so we're going to do plus. So y equals 600, parentheses 1 plus 4 divided by 100 is 0.04. And that's our equation. And then it says find the balance after 12 years. And carefully put that into your calculator, and you'll get $960.62. Okay, example 3. This one has a twist to it. It says, how much money do you need to deposit in an account that pays you 9% interest compounded yearly to have a balance of $12,000 after 8 years? Well, we can write our equation here, but the thing is well, actually, let's not, it doesn't say to, so let's not bother. But what I want to get at here is they're not giving you the initial amount. They're telling you the end amount. Our end amount is y, okay? And so they're saying we want y to end up being 12,000. And they're asking how much would you have to deposit? And 9% is 0.09 into an account that pays 9% after 8 years. This is what they want you to do here, or this is what we're going to have to do in order to get C. So to get C by itself, it's tempting to punch this into your calculator, and then, but what you're going to end up doing is dividing it into 12,000, and that gets tricky with your calculator. So here's what I would like for you to do. Divide by that whole thing to the other side. And now, even with this calculator, we should be able to do this in our calculator just fine, as long as we write it as 1.09 in our calculator. So check this out, 12,000 divided by 1.09 to the exponent of 8 equals. And so even your more basic sort of calculators like mine will do this without any problems. If you have one of those fancier calculators, you could enter this all in, just make sure to include your parentheses. All right, so they would need to deposit approximately $6,022.40 in order to get $12,000 after 8 years, leaving the account alone. So yeah, it's kind of cool that you could plan ahead. You may know that you're going to have a $12,000 expense at a certain time. Well, you don't have to spend all of that. You do a lesser amount, invest it, and then have that 12 grand when you need it. So it's kind of an interesting idea. So yeah, just to be clear, those divide out when we do that. Okay, example 4. I would encourage you to read through this and see if you can figure it out yourself. But 0.5 divided by 100 is 0.005. That part right there, I just want to give you a heads up. Some calculators will give you this in scientific notation, but I hope you're seeing a pattern here. You move the decimal place 2 to the left to get your rate. All right. But yeah, this is talking about it, let's see. Oh yeah, decreased. Okay. So I think I'm ready to write my equation. I think I've got this figured out. All right. So y equals, so 41 million acres to start out with. So at the end we'll say million, with our answer. And then 1 plus, nope, not plus, is it? It's decreasing. So we'll do a minus 0.005. And then here's the thing. They want us to find out how much forest is left in 2002. Well, we got to know how many years that is. Well, they started in 1963. So 2002 minus 1963 is 39 years. 39 years is taking place. And I'm going to punch that into my calculator. 41. I guess I could do that. Well, no, I'll start here. 1 minus 0.005 equals that. Exponent 39 times 41. So 33.72 million acres. Thanks so much. Have a good day.